this video, we're going to learn how to select a statistical test in just 6 easy steps. So with all of the different statistical tests out there, how do we know which one is most appropriate for our data to answer our research question? In this video, we'll begin to answer that question. Before we get started, I want to talk about who this video was made for. This video is best suited for someone who's had at least one statistics course in the past and is somewhat familiar with statistical tests, but maybe who's having trouble seeing the forest through the trees of all of the different statistical tests out there and doesn't quite know where to start to choose an appropriate statistical test for their data and research question. Let's start with the 6 steps. We'll just go over a broad overview now, and then we'll go into each step in more detail over the course of this video. The first step is identifying the variables in our research question and the role that each variable plays. So, for example, if I'm interested in whether age predicts a personality trait such as neuroticism, the variables in my model are age and neuroticism. But I also want to know the role that each variable plays. Which one's the predictor, which one's the outcome. To do this, I need a solid understanding of my research question. Next, I need to identify the scale of measurement for each variable. We'll talk about what this means in a moment, but in order to do this, you'll need to have a solid understanding of how each variable was operationalized. This just means how did you measure or manipulate each variable in your study. Once we've answered 1 and 2, we're ready to choose an appropriate statistical test. For example, we might decide to use a decision tree like the one I'll show you in today's video. Once we've selected an appropriate statistical test, or if we've decided we're still not quite sure which statistical test is best, it's time to move on to step 4. We need to decide whether we have enough experience, expertise, and comfort with the statistical test that we've chosen to conduct the analyses ourselves, or if we need to learn more or ask for help. Then we need to check whether the relevant statistical assumptions are met. In other words, do our data fit all of the requirements necessary for the statistical test that we've chosen? And finally, once we've chosen an appropriate statistical test, we've either decided to run the analyses ourselves or found a collaborator to run them, and we've confirmed that our data meet all of the necessary statistical assumptions for the test we've chosen. It's time to run our model. Let's dive deeper into this first step. Identify the variables in your model and the role that each variable plays. Here, I'm referring to whether your variables are the predictor, the outcome, or maybe a control variable. Your outcome variable is the variable being explained. This is also sometimes called a dependent variable. Outcome variables always must be measured or observed, meaning that we can't manipulate our outcome variable. Predictor variables are the variables doing the explaining. They're explaining or predicting your outcome. These are sometimes called independent variables, and they can either be measured or manipulated, like in the case of an experiment. But how do you know which variable is the predictor and which variable is the outcome? Sometimes this is decided for you by the way that your data were collected. So for example, if one of your variables was manipulated and the other was measured, the variable that you manipulated necessarily is the predictor. Similarly, if we collected our data longitudinally, and the predictor comes before the outcome variable in time, it must be the predictor. We can't predict something backwards in time. But most of the time, you'll want to make this decision based on your research question and your hypothesis. Which variable are you trying to explain, and which variable do you think might do the explaining? Finally, there's one other type of variable that we might want to consider, and that is a covariate, also called a control variable or a confound. A covariate, control, or confound is still technically a predictor variable, but it's not necessarily our key variable of interest. Instead, it's another variable that we expect to be related to both the predictor and outcome that we want to account or adjust for. Next, once we've identified the variables in our model and the roles that they play, it's time to identify the scales of measurement for each of those variables. For example, we might have continuous variables. Continuous variables are measured on a quantitative scale with equal intervals between points. This means the distance between 1 and 2 on this scale need to be the same as the distance between 2 and 3. You might have learned about ratio or interval scales in previous courses. Both of these can be considered approximately continuous. Examples of continuous variables are things like age, reaction times, symptoms on a continuous scale, and oftentimes we can treat Likert-type scales as approximately continuous. Likert-type scales are the scales where you ask someone, for example, to agree or strongly disagree with an item on a scale from 1 to 7. When we have multiple Likert-type items that we average together to form a composite, we can usually treat it as approximately continuous. In contrast to continuous variables, you might also have categorical variables. Categorical variables can be either ordered or unordered categories, but the distance between the categories is not known. So, for example, you might have 3 different experimental conditions that you want to compare, such as a control condition, intervention A, and intervention B. These are 3 different categories, but there's not a clear distance between them. These are either nominal or ordinal scales. Nominal is the instance where the categories are unordered, and ordinal is the instance where the categories are ordered. And finally, you might have a special case of categorical variable called binary or dichotomous. This just means that there are 2 categories rather than 3 or more. Lastly, there are special types of variables that might not cleanly fit under either continuous or categorical. One example that might come up in your research is a count variable. This is where we're counting whole numbers. For example, the number of doctor visits in a year or the number of children that someone has. We often have to treat this in a special way in our statistical models. Once we have answers to 1 and 2, we know what types of variables we have, the role that each plays in our model, we can choose an appropriate statistical test, and we can use decision trees to help us do this. In this video, I'm going to show you one simple decision tree, but there are many others out there that you can find with a quick Google search or by referencing statistical textbooks with varying levels of complexity for the types of research questions that you conduct in your own research. So let's take a look at the decision tree that we'll be using today. The first decision we have to make is whether our outcome variable is continuous or categorical. If we decide that our outcome variable is continuous, we likely can use a family of statistical tests called the general linear model. Now, within the general linear model, we often want to specify the exact test that we're going to use. And to do that, we need to know whether our predictor variable is continuous or categorical. If our predictor variable is categorical, we'll use a t-test or an ANOVA. If our predictor variable is continuous, we'll use linear regression. Going back to the top of the decision tree, if our outcome variable is categorical or some other special case besides continuous, we will instead need to use the generalized linear model. Now, these two terms are very similar, general and generalized linear model. The general linear model is what we will most often use when we have a continuous outcome variable, and the generalized linear model is what we will most often use when we have a categorical or some other distribution for our outcome variable. The generalized linear model includes many different tests that differ based on the distribution of the outcome variable. I want to talk a moment about the assumption of normality. The assumption of normality underlies the general linear model. General linear model assumes that the residuals, or the errors, from our models are normally distributed. This is sometimes but not always true for continuous outcome variables, which is why we can often use the general linear model when we have a continuous outcome variable. So let's zoom in on linear regression. This is the type of model that we will use when we have a continuous predictor and continuous outcome. There are many different forms of linear regression. We have simple linear regression, or simply a correlation, when we have one continuous predictor and one continuous outcome, such as in my earlier example of age on the one hand and neuroticism, perhaps assessed with a Likert type scale on the other hand. We can also have multiple predictors, and then we'll call this multiple linear regression. This is where we have two or more continuous predictor variables and one continuous outcome variable. Here we might be interested in the unique effects of both age and health status on neuroticism. Finally, we have ANCOVA, or analysis of covariance. This is an extension, just a special case of multiple linear regression, where we have a combination of continuous and categorical predictor variables. Sometimes the term ANCOVA is used when our key effect of interest is the categorical variable, and we just want to control or adjust for the continuous variable. But other times people use this term anytime they're referring to a model with a combination of categorical and continuous predictors and a continuous outcome.